Hello everybody, my name is Adam Cankaya, and today I will be talking about underwater Bluetooth sensor mesh networks. So first, a few quick words about what exactly Bluetooth mesh networks are. So a Bluetooth mesh network is a collection of devices, of Bluetooth devices, that are spread out and interconnected to each other to form a network. The standard put out by the Bluetooth Special Interest Group defines a managed flood-based mesh network approach, which means that any node in the network can send a message and communicate with any other node in the network. The only restriction being that the node sending a message has to be within range of at least one other node in the network. And then this message will be passed along the network until it reaches the destination node. The mesh standard also incorporates network and application layer keys, so that we have encryption and authentication implemented so that nodes can be authenticated. Nodes can form private subnets so that a group of nodes can communicate with each other without the rest of the network being impacted. To prevent the network from getting overwhelmed with messages, there's two different ideas are implemented. The first is the message cache list, which is basically a list of messages that have been delivered to their intended recipient. Which means anytime a message is received by a node and it's looking to forward it along, it first checks to see if the message has already been delivered and if it's already on the message cache list. If so, it does not forward it because it's already been delivered. And then there's also a time to live value, which is a set number that is basically the number of nodes that will relay a message in an attempt to reach the recipient. So the message will only be relayed, say, 150 times total, as opposed to being relayed over and over again in an attempt to reach a node it's impossible to reach. And of course, each individual device can have multiple instances of itself running at the same time, so that it can actually act as multiple devices simultaneously being part of multiple mesh networks, either public ones or private subnets. A bit about how electromagnetic waves travel underwater. The propagation of EM waves is dependent upon the signal frequency and the physical properties of the propagation medium. Generally in air or vacuum, we don't really worry about this, but underwater, especially in salt water, these properties are highly effective on a signal's ability to propagate. The big one here being the electrical conductivity, sigma, which goes up with higher amounts of salt in the water. The higher the electrical conductivity, the higher amount of attenuation the signal will experience, and the shorter propagation distance. So what I wanted to do was look at how some other people have proposed to overcome this issue with EM waves propagated underwater. So the first paper I looked at signals in the ultra wideband range between 500 megahertz and 1 gigahertz. This is a bit smaller frequency than the traditional Bluetooth 2.4 gigahertz signal. These authors conducted simulations with various shapes of antennas, and for saltwater found the best performance was this ribbon twisted in 10 times 30 degrees into a loop. And this is for the average ocean salt water of 4 Siemens per meter. And the way they determine this best performer is by looking at the minimum return loss value at various frequencies. Here the return loss is on the vertical chart in decibels. The various dashed lines are different angles and length ribbons, while the solid red line is the best candidate they found. And you will see there's a pattern here, return loss minimums, that repeats itself every 100 or so megahertz. And this pattern is repeated at all frequency ranges in all shapes of antennas. That's an interesting find. The second paper I looked at was more experimental, using real-world antennas in water. These signals are at a much shorter frequency, 10 kilohertz to 20 megahertz, still in the radio range, but much smaller than Bluetooth frequencies. So their antennas are a little bit physically bigger to accommodate those larger wavelengths. And also these antennas physically rest on the sandy seabed. They're not floating in the water. And so their presence on the seabed allows there to be a less lossy medium for the signals to propagate, with a smaller electrical conductivity, reduced attenuation, and thus a much longer propagation distance, using the sand as the propagation medium. So they conducted some experiments using loops and dipoles. They found that the loop antennas had the best performance, particularly the 40 centimeter radius loops. On the left here are some results, both the simulations and the dotted lines they did, computer simulations, and their actual experimental results with the solid lines. The different colors are the distance apart for the antennas, and the vertical axis is the attenuation, and the horizontal axis is the frequency. The yellow and orange are the farthest apart antennas at 12 and 13 meters apart, so they experience the most loss at the smallest frequencies, while the black line is the shorter distance, only 8 meters apart between the two antennas, so they experience a smaller attenuation even at higher frequencies. What you will note here is that for all of these results, the higher the frequency, the larger the attenuation. And of course, the farther apart the antennas are, the larger the attenuation. The chart on the right shows the distance apart between antennas at their distance for minimum attenuation. The distance is on the horizontal, and the vertical is the frequency. So as you can see, higher frequencies require a much shorter distance apart. So even at something as small as 40 kilohertz, you're still looking at 3 meters apart or less for the minimum attenuation distance. And keep in mind, all of these results are greatly enhanced by the presence of the sandy seabed. Most of this wave propagation is happening through the sand, not the water. Final paper I looked at RFID tags and their usage underwater. The paper provided this formula that's a rough calculation for the attenuation as a function of the frequency, which seems to agree with the other paper's results. Basically, the higher the frequency, higher the electrical conductivity, the more attenuation. The authors also provide a formula for this term called the penetration depth, which they call an upper limit on how far a signal will be able to propagate in a lossy medium. For a typical 2.45 gigahertz Bluetooth signal, you're looking at a penetration depth in salt water of less than 5 millimeters. Because of such a tiny propagation distance, penetration depth, the authors instead consider RFID tags that operate at much smaller frequencies, such as 125 kilohertz, that give a penetration depth of about 7 centimeters. And so the authors provide several real-world applications going on now of RFID tags underwater. On the left here is an aquarium exhibit where the fish have all been tagged with RFID tags, and as they swim by this large loop antenna on the display there for guests, it tells you the fish's name and species and provides information to the scientists there about the fish's swimming and speeds, distances they've traveled, etc. On the top right here is the intertag system that RFID tags are placed on pipelines underwater. When crews come along to repair them or inspect them, they upload this information to the tags, and then crews that come later on can read that information, read that data off the tags. And then finally down here at the bottom is a research project called the Smart Pebbles system, where they take rocks, put RFID tags inside them, release them on the shoreline, and then over time the scientists go out and track them, see how their distribution is changing over time, and use that to track the erosion patterns going on. So what all of these papers have basically concluded is that traditional Bluetooth signals in the 2.45 gigahertz range will only propagate at most a few millimeters. We really need to reduce the frequency down to the low end of the radio range if we want to have a propagation distance of even 10 centimeters. Given these short distances and the overall challenging environment that is the ocean, any kind of mesh network is going to need to be able to adapt to this lossy medium and a topography where the nodes can be shifting their physical position at any time. Things like disruption tolerant networking and forward error correction are really going to be necessary to allow nodes to communicate in the short time that they're within range of each other, and ensure that whatever data they get will be useful to the node. This is really the only way the network will be able to maintain any kind of connectivity. Any questions or comments, please post them and I will respond soon. Thank you, everybody.